Good morning, everyone. I am Thierry Wastiaux from Interface Concept, and today our presentation is about innovative thermal management in VPX system. Clearly, in VPX systems, the customers and the system designers require more and more processing power from their VPX system. It means really getting the maximum processing power from each slot of the system, of course. The thermal management cannot be anymore an afterthought. You cannot design anymore, make a smart electrical hardware design and then try to cool it. You have to introduce the, let's say, innovative new thermal techniques right at the beginning of the design. And this is what we are trying to do. So how to do that? Basically, Interface Concept has developed fluid and thermal simulation models. And these models have been validated through experiments. And this is very important for accuracy of these models. And these high precision simulations allow component placement, and thermal interface design. So it allows, in particular, to improve the air cooling solution, air-cooled solutions. So let's look at a VITA standard, which is the 48.1, which defines the mechanical specifications for air-cooled VPX plugins. So what we have tried to do here, we have tried to improve the cooling of the VITA 48.1 compliant products to extend the temperature range of operation. So the goal was to drive the cost down, of course, and also to avoid the use of less effective solutions, less cost-effective solutions, like the VITA 48.2, which is for condension cooled, or VITA 48.5, which is specifying the airflow through standards. One of the advantages of the air cooling solution is that you also cool the PCB and the components at the bottom of the board. And as you know, as we are putting more and more on a board, you are also putting components at the bottom, more and more components at the bottom of the board. So basically how we do that? First, we optimized the airflow path. We have discovered that there is a lot of waste in the airflow thermal capacity. So improving the airflow path is critical. Second, we have also introduced new techniques in the design of the heatsink. And the third point, we have also optimized the thermal contacts with the components. So it's a lot of, let's say, elements which are put together using the simulation tools. A good example of this is this product, which is a 3U VPX board using an Intel Xeon D processor, in this case the 1599. This kind of processor constantly adapts its operation scheme to stay under the junction temperature. It means that if you increase the cooling of the processor, you will also get more power from it. So you get more power up to a certain level, of course, to a limit, And this limit is called the TDP, the thermal design power. And this is basically the average power of the processor dissipates at base frequency and, let's say, with all the core active. So we have, if you look at this, this slide here, you see a comparison between a classical approach and an enhanced approach, an enhanced design, I would say. You see here on this curve, you see here on this slide, the maximum processing power the processor is able to reach. At this level of TDP, the user gets the maximum processing power. So the goal is to reach it as much as possible. So we have considered here let's say, we have taken two assumptions. The ambient temperature at 55 degrees and the ambient temperature at 70 degrees. And you see, first of all, that at 55 degrees, we have basically reduced the airflow need by half. You see here 30, the unit is cubic meters per hour. This is a European unit. And you see that you divide this airflow by 2, basically, at 55 degrees. You also see the red lines. You see here that with a classical approach, you cannot reach at 70 degrees. You cannot reach the maximum power. You never reach it. So you see that with the enhanced design, you can reach this maximum power. And this is reached at this airflow here. So this is another let's say, test which has been made at 75 degrees. And you have here another slide which presents another operating point, which is at 30 watts at 75 degrees. You see here again, on the left of the slide, you see here that we are at 30 watts, and you see that basically we are able to divide the airflow by more than 2. So from 50 to 20 cubic meter per hour. You see also, and as importantly, you see that if you look at the difference of pressure between the input and the output of the airflow, you see that also we are able to divide this by 2. So coming from 50 to 20. So roughly you divide by 2 the airflow, you divide by 2 the difference of pressure, meaning that roughly you divide by 4 the power of the air cooling system. So for a chassis, it is very important. So of course, we are working on air cooling techniques, but we are also working on, let's say, the VITA 48.2 for condension cool. And we have, so this is an example of test bench here for these 3U plug-in units. And Interface Concept have developed for the VPX 6U board a new cooling system. And this is for the 48.2 standard for condension cool. And you see here on this picture that basically with this new system, we are able to, compared to a classical aluminum heatsink, you are able to reduce the, let's say, the resistance of the heatsink by a factor of 7. So it means that you need only you need only here 3 degrees Celsius between the heatsink and the chassis, instead of here 25 degrees. So this is a big improvement. And this is now available. So basically you see that it is very important to keep on investing on cooling techniques in this VPX world. And this is what we are doing in Interface Concept. So this is the end of my presentation. Thank you.